So my intention was that I'll just say something about the problem that I'm interested in, structure for motion, and how that relates to factorization. And then I'm going to present a class of relaxations that I've been working on for a while now to solve. They apply both to sparsity and rank penalties. I will talk a little bit about those and present some theoretical results that apply if you have this well-known RIP constraint. And then if I have time, I'm going to go into a way of optimizing these relaxations with a bilinear parametrization and some theoretical foundation for doing this, and present some results in terms of structure for motion. But we'll see how far I get. So this is yeah, a very short summary of what structure for motion is. So basically you have a set of images of some kind of scene. And from those images, you want to reconstruct like the scene shape in some sense, and compute where were the images when I captured, where were the cameras when I captured these images. And the way you do it is you track points in these images. So I have some red points here on the dinosaur, and these are being tracked. So I record their coordinates, and I get the tracks like this. And then I put all of these tracks in some kind of measurement matrix. And from that matrix, I try to use some kind of geometry or something to extract this. If I have something which is called an affine camera model, which I don't really have time to go into this, but it's roughly like an orthogonal projection, except you can have scalings and skewing and things like that. If that's the case, then the measurement matrix factorizes into two parts. So one part which consists of information about the cameras, and one part which consists of information about the 3D points. So here it's basically the 3D point coordinates, and here it's what's called the camera matrix, which basically encodes orientation and position of the camera. This is a bit simplified. So the affine camera model is a rough approximation of a real camera. So we do have nicer models than this, but it's essentially a factorization problem. Yes, and of course, since this is a real problem, what we observe is not the complete measurement matrix. We have noise, and I would say the most significant problem is the missing data. So when we track points like this, we will only be able to see them for a couple of images, either due to occlusion or limited field of view or something like this. So we're able to detect some point in some image, and then we track that for a couple of frames, and then it's going to disappear again. And this typically gives rise to like band structures like this. So along the diagonal, we might have data. So this is really the data we have, and from that we want to extract the factorization. And once we have the factorization, of course, we do have the elements as well. So I want to emphasize a little bit here that it's really the factors that are interesting here. Those are the ones that we are looking for. We do get like the matrix here as well, but that's not the primary thing that I want. So this is a little bit different than other image like problems with in-painting or denoising, image denoising and things like that, where you're primarily interested in recovering the pixel values or something like this. So if you have some kind of singular value penalty, it's not essential that you really reach that low rank that you want. But here, if I don't have the right rank, then these factors are not going to be of the correct size, and I won't be able to interpret this as a rigid scene any longer. So I think that's, yeah, that's an important thing to have in mind when you solve these. Okay, so what I'm really interested in is also what happens when this scene has deformations. So let's see if this works now. So here is one example of a moving camera and a scene that's deforming. So we have both motions in the scene and motions from the camera. So this makes the problem much harder. In terms of modeling, you can model this by adding a weaker rank penalty. So in this case of rigid, it's usually 3 or 4, depending a little bit on the camera model. But for these non-rigid scenes, it's more than that. And basically, the rank gives you a measure of how complex the deformation is here. And of course, here, when we have higher rank, we will be much more sensitive to missing data and things like that. But this is the problem that I'm really interested in, and I'm aiming for this, even though I'm pretty far from doing this yet. All right, so let's get into this framework then. So this is something that I've been working on for a while now, and it's been motivated by structure from motion, but like I said, I'm not quite there yet. So usually I look at problems like this. So we have the usual suspect, this least squares term, some kind of data fit, and then we have some kind of regularization. So a penalty of the cardinality or the rank. So here, both cardinality and rank is going to work. The results will be almost identical. So this G function here is nice in some sense. So it's a sum of positive increasing distances. So if you plot this as a one-dimensional function, you get this nice convex shape of the G function. And the difficulty is when I insert into this one, I insert the cardinality function, for example, then we get these strange, like constant functions almost everywhere. So here, for example, I have, it's 2, and then on the axis, it's 1, and then in the origin, it's 0. So yeah, very discontinuous and hard to work with in optimization. But yeah, you all know this, I guess. Right, and the analogous low rank formulation would be something like this. So instead of cardinality, I just insert the rank here, and I have a linear operator on the matrices instead. But essentially, this is the same. So these are some standard examples. If I have GI is constant, then this is what I get. So I get a soft rank penalty plus the data fit term. Here's another example. So if GI is 0 up to a certain K, and then infinity, I get this hard constraint. So minimize this data term with the constraint that the rank is less than K. Infinity is fine. You can work with that. You don't have to have like large number or anything. You can work with infinity here. All right. So I would like to say something also about bias, even though most of you probably know this. So the goal here, when I have a problem like this, so this is some regularization here. So for example, if this is rank, well, this is now a one-dimensional problem. So this is just either x is 0 or it's non-zero, and then the penalty is based on that. So what I would like to recover here is the B, right? So I would like to get the B back if it's large enough. If it's small, then it's should be classified as noise, and then I should get 0, right? So for a large value, I would like this to remain unchanged. So if I take a general regularizer here, and I just minimize this, see what it gives. So the minimum is either going to be in 0 because it's non-differentiable in 0, or it's going to be a stationary point, which is a solution to this basically. So if I look at this, the only way I can recover B is if this derivative here is 0 or really small or something like this. So when I have a large X here, I would like the derivative to be 0. Then I won't get any shrinking of this B that I'm trying to recover. So this is what's led to all of these non-convex approaches to regularization, I would say. Yes, okay, so the nuclear norm is one example of this. If you do have a lot of noise and you need to suppress that, if you do it with a soft rank penalty like this, so these are now singular values of the matrix X0, the yellow ones, and then the blue line is the square root of mu, which is the threshold basically. Then what you'll get are these red bars. So these will be the optimal singular values for X. So this, which is below square root of mu, is classified as noise and suppressed, and this is left unchanged basically. But when you have this bias, what happens is that you subtract from both this noise and from the signal, you will subtract basically the bias, right? Of course, this is an extreme case with lots of noise here, but so whether it's worth going to something bias-free or not kind of depends on the situation, whether you have lots of noise or not. For structure for motion, it's really essential to try to do this, to go to bias-free approaches. So this is one example. So this is the solution with the nuclear norm. So what happens here is where I have these elements, I guess the problem here is that they are highly correlated, the locations. So along the diagonal here, I have smaller errors. This is the difference between the ground truth solution and the solution I get from the nuclear norm. So it's good where I have these elements, but out here you start to get larger and larger errors. And if you look at the trajectories, so these are the completed trajectories, what you see is that they're being stretched towards this point here. And this point is the origin of the image. So when I stretch these trajectories towards 0, it becomes more happy, the nuclear norm, because it likes stuff to be 0. I should say that this is a really hard problem, and I mean, my approach doesn't necessarily converge to the correct solution here. In fact, I don't even know if there is a bias-free formulation that doesn't have local minima here. But this is, anyway, this is what started me down this path. All right, so what am I doing? This is a description of how I relax these problems. So what I do is I take this regularizer, I add a quadratic term to it, and then I compute the convex envelope of this new function f. All right, and then I take this convex envelope and then I subtract this quadratic once again. This is apparently called the quadratic envelope. Somebody informed me about this. This is an old name, so it's not due to me. Right. So the regularizer is not convex. But the hope here is that it's going to work well with quadratic terms, because when I add something quadratic, it's going to be almost like this convex envelope here, very, very loosely speaking. Okay, so this is my regularizer, and then I try to solve problems like this. This regularizer is independent of permutation. It's invariant to permutations. So it only depends on the sorted magnitudes, on the magnitudes of the elements of the vector, or in the matrix case, it just depends on the singular values, basically. So there is an automatic permutation in this expression. Right. So unfortunately, there is no, as far as I know, there is no closed form solution for this function. So except in one case, if all these g's are the same, so I have this constant soft penalty, then there is a closed form solution. But to evaluate this this regularizer, I need to solve a concave maximization problem. It's easily solved. You can reduce it to a one-dimensional search over a concave piecewise quadratic function, basically. And so you need to search it over certain intervals. But that's really quick, and in fact, it's much more expensive to compute singular values, for example, which I need here. So this is not the bottleneck in any case. You can also do a proximal operator. You can compute the proximal operator of this one almost in exactly the same way as you do when you evaluate this. Right. So here is one example of what it looks like. So this one-dimensional version. So GA is 0 when x is 0 and 1 otherwise. So this is my unrelaxed version, and here is the relaxation. And this is the expression for it. So these are the same, except when I'm in this interval here. And this one here, that's basically the threshold where I, if I were to solve a quadratic problem like this with this g, I would get x should be b if b is larger than 1, otherwise 0. So I don't want to, I can't, if I have solutions that end up in this open interval, then the regularization is going to be different. And in the general case, the corresponding constraint looks like this. So it's square root of those g's that I had. This normally is not a problem. So this usually doesn't happen. And you can, in fact, derive constraints that guarantee this, but I'm not going to go into this. So before I present my results, I want to also mention something about this non-separable thing. So this general framework contains regularizers that are not separable. And by separable, I mean that if I have a one-dimensional function like this, and here's the relaxation, I could apply that to all my singular values or to all my elements in the vector or whatever. I would get something which is bias-free because it's constant above some threshold, but I get something which is really uninformative for high cardinality vectors. So if I know that I'm looking for something with low cardinality, but I don't know exactly how low, what I could do is I could add some constraint here, something that counts the number of non-zero singular values or elements to this, and say I don't want that, and then relax it, and then I get this relaxation instead, which has this nice gradient in some sense. So it's heavily going to penalize these high cardinality functions. And this is what I like with non-separable. They're able to more or less count the number of non-zero singular values. It's not just based on the size of the singular values. Okay, right. I think I'll. Okay, so you can prove a bunch of stuff about these regularizers. For example, they have if you have a bounded operator norm bounded by 1, they have the same global minima as the unrelaxed version. All the local minimas of the relaxed version are also local minima for the unrelaxed one, but not the other way around. Typically, you have much fewer local minima here. So what I've been doing is I've been analyzing this under the restricted isometry property, which I guess you all know. So here I have to mention that for my structure from motion problems, this doesn't hold. So this is purely out of theoretical curiosity, really, and people seem to be interested in this. So that's why I went into this. And the intuition here, the intuition is, so if something like this holds, then it's almost like AX is going to behave similar to X, right? So, well, yeah, this one behaves similar to this one. And for this one here, so if I have a term like this plus the regularizer, this is actually a convex envelope, because when I computed this, I took the convex envelope and I subtracted a quadratic. Now I'm putting it back again, so I get convexity here. So if I just take something that behaves similar to this, does that mean that there is some kind of near convexity here or something like that? At least for vectors that have low cardinality, right, where this holds. I mean, very, very loosely speaking, and this is what I am trying to show, that there is something like this. And basically what I'm doing is I'm studying the stationary points of expressions like this. What kind of stationary points can there be? So before I present the main result, I just want to give you some more intuition on what to expect here. So if I have something like this, so now again, it's a one-dimensional problem. This 1/2 is what corresponds to the operator here. So what I've done here is I've plotted the original function, the blue one, and the relaxation for different values of B, to highlight that the properties here are going to depend on the data. So if I have something which is clearly, I mean, it's 0 from the start, or it's really small, then I have a unique local minima down here. It's definitely clear. If I start to increase the B at this point, we're going to get a new stationary point here, right? If I keep increasing it, so here B is 1, then we have 2 global minima that are yeah, equally good. And then if I keep increasing it, yeah, so here it's still a stationary point here in the origin, but this is like the highest value. If I increase it even further, then there is only one minima somewhere to the right here. So there will be local minima sometimes, and whether there are, how they are distributed depends on how ambiguous the data is. If we have really ambiguous data, we cannot hope to do some global optimization here. Right. Okay, so the main result is coming up. Okay, so I'm studying stationary points, and the way I do it is I put back this quadratic. I look at this convex function and this differentiable function. This one is nice in the sense that it has a subdifferential. So these are the stationary point equations. And this is what the gradient of h amounts to, right? So this said here, this is what corresponds to my b roughly over here. So that it's properties of this said that's going to tell me whether there can be other stationary points or not. And it's easy, I'm saying easy, yeah, it's pretty easy, I would say, to show that this stationary point x will be a solution to this problem. So this is now again the convex problem. That means that x is a thresholding of z. So I just take z, I threshold it at some point, and then I get x here. And the result that I have says that if the elements of z are not too close to the threshold, then this is going to be, in some sense, a unique stationary point, right? So yeah, it's a really technical result, but I hope I've given some intuition about what it says. So the first line here is basically stationary. We have a stationary point, and it has cardinality k, and we're not falling into this region where the regularizer is not the same as the original formulation. So then if the elements or the singular values of z are not in this interval, so this is now the threshold gk, square root of gk. So I have to be a bit above gk or a bit below gk for all of them. And there has to be a gap. So k here is the last non-zero, last element where I have non-zero x. So the next one here, there has to be a little bit of a gap here. So the noise has to, in some sense, be distinguishable from the signal. Then any other stationary point has to have a certain cardinality. And like the strength of this depends on what kind of rip you have. So what if this R, for example, is really high, then that means that, yeah, this is high. So any other stationary point has to be of high cardinality. So yeah, one example is if K is less than R over 2, then this stationary point is the sparsest one you can find. There could
Carl,
still be.
just wanted to give you the 5-minute warning.
Yep. Okay. So I'll wrap up. Thanks. Blah, blah, blah. Okay. So the results, yeah, I'll skip these results, but this is too. So the previous one was just, this was what I talked about. This just says if there is such a point. Then we have one which guarantees that there is such a point. But I'll skip that. And yes, so far I've only said stuff like if this stationary point has a certain cardinality, every other point has to have more. So I'm not really able to exclude high cardinality points here. Why is that? I mean, conceptually, the restricted isometry property only says something about the sparse points. So it's really hard to say something about the non-sparse ones using properties of this one. Yes, and as I said before, when I have separable formulations, I have regularizers that are very uninformative for high cardinality as well. So there is really nothing here that I can use for high cardinality points. So I have to restrict myself a bit to be able to say something. And skip this. the way I do is then by adding these constraints that if I have, I'm not interested in cardinality larger than K max, for example. Then I put these G's to infinity and I get this nice gradient that I can work with. And you can prove that if, for example, if this operator is bounded, then the stationary point I've been talking about is going to be unique. You have to have some technical things as well, but essentially that's the result. Okay, skipping ahead, maybe yes, okay, so I'll do this experiment as well. So here is an evaluation of these two methods. So the blue one is G is constantly mu. The other one I've added one of these hard constraints. I'm not interested in anything that's above 10. And yeah, this is how I generate the data. And I'm optimizing this from starting point 0. This is optimized with ADMM, by the way. So here there is no difference whatsoever. They give exactly the same result, and they seem to find what's the global minimum when I start from this point. If I change the starting point to this least square solution, which seems like a sensible thing to do, then all of a sudden things get worse. So now the blue one gets stuck in high cardinality points. And indeed you do get, like, this is the distance to ground truth, and this is the objective value. So you do get really bad solutions here, which is, to me, this was a complete surprise when I saw this the first time. But the yellow one is able to recover. You can do even worse. If you take the least square solution, you add a vector that's in the null space of A, and you make it big enough so that all your elements are larger than this threshold square root of mu. So then this point will be a solution to the least squares problem, just a data term. And the regularizer will be constant locally around that point. So nothing happens really. But the yellow one is going to recover from this, which I think is nice. Are there other local minima? I don't know. These are the ones I've found, and these are the ones I've been able to construct in some sense. Okay, yeah, skipping. I have used this for structure from motion problems, and it seems to work. It doesn't work for the dinosaur problem. That's quite hard, but I've done it for a couple other, well, quite a few other data sets where you have less missing data. But for the dinosaur, I'm still running into local minima. I think I'll stop here then.
Thank you very much, Carl.
Thank you.
Are there any questions?
So sorry. So let me make sure I understand what exactly this is proposing. So you're minimizing this auxiliary function, and you're going to use like regular optimization to optimize it and get a local point, right?
Yep. Yep.
And what is what does the theorem that you have in there, like, actually predict, or well, somehow, I mean, how do I under?
Yeah. How do you? Well, I mean, it's not able to predict that we're always going to end up in the global minima, because it's not true, right? So there will be stationary points. It's kind of predicting that it's saying something about the distribution of those stationary points, or maybe the qualities of those stationary points. So what it's saying essentially is that if you find a stationary point, so you optimize, you end up in a stationary point which is sufficiently sparse or has sufficiently low rank, then all the others have to be of high rank, right?
And somehow, why is that? Okay, and somehow that tells me that that's a solution that I really want. Is that the?
Well, normally yes, but I mean, I can't. I would have to have something else to be able to say that this is the global optimum. But I mean, normally it seems like you would be looking for like a very, if you're minimizing some kind of rank regularization, you probably want a low rank solution, right? You're not interested in any high rank stationary points.
Mm-hmm.
So maybe you could use it like one of those try, like hit and miss or whatever, like just try minimizing. If you get something which is low ranked, then that's probably it. That's probably the global minima. If you get something which is high ranked, then yeah, I don't know. Then we don't know anything. What I'm saying now is a bit strange, because I mean, we don't know if this RIP holds or not. We don't know how strong it is or for what ranks or whatever. So in practice, I would say this is, I mean, it's not that useful.
Sure.
Maybe if you're really interested in these problems where you have some kind of asymptotic growth or something, you really have lots of elements, then maybe you can say something about that. I'm not really an expert in that. But so my goal is to like I said, so the structure for motion problems, you don't have RIP. So this was just purely theoretical, but my goal is to extend this to missing data problems as well.